Yeah, yeah. So you're watching the recording. I missed 5 minutes at the beginning. I'll do the same lecture tomorrow, so look at that one if you need to see it. So summarizing that last slide, as you're boiling or as you're freezing or melting, the temperature is constant, okay? So all of the energy is used to vaporize the liquid. And again, remember that we learned that boiling is occurring when the vapor pressure of the liquid has equaled the pressure of the surrounding atmosphere. That's what makes something boil. When you've heated up something to a high enough temperature that their vapor pressure has increased so much that it's equaled or gone above the vapor pressure, the atmospheric pressure. Melting point is a little bit more, well, it's not that complicated to describe, but melting point is also an idea that the temperature is constant while melting occurs. What is melting? You're breaking your molecules from their crystal lattice positions or lattice points, and now they can move around. They're not completely breaking the IMFs. If you want to equate, well, what is melting when it comes to vapor pressure, we haven't even talked about this too much, but even solids have a vapor pressure. So what does it mean for a solid to have a vapor pressure? Well, solids, even in solid form, emit little particles of gas. That's how things sublime. That's how ice cubes kind of disappear over a long period of time in your freezer. And so everything has a vapor pressure so solids have a vapor pressure. And just like vapor pressures of liquids, if I increase the temperature, the vapor pressure of the solid will go up. And technically, the melting point happens when the vapor pressure of the solid is equal to the vapor pressure of the liquid at that particular temperature. And don't worry about that. That's like a weird concept, but just in case you were curious about it, that's how that works. So let's talk about another graph that when you talk about phase changes, we like to look at. So we had heating curves, we got vapor pressure curves. This is a new one. This is called a phase diagram. And I think it's like one of the more interesting ones, although we haven't shown you the phase diagram yet. So the thing to remember about when we see this next thing is remember that phase equilibrium is when you've got both substances, like a solid and a liquid, occurring at the same time. And what I mean by at the same time, I mean solid is turning into liquid, liquid is turning back into solid, and the rates at which they're doing this are approximately equal. So you'll always have a little bit of both. All right? If the rate at which solid turns into liquid is greater than the rate at which liquid turns back into solid, eventually everything will be a liquid. So it's melting. But when the rates are the same, you'll have both. They'll just continue like that. So that's what we mean by phase equilibrium. And you can have that condition where you'll have both in existence. If you keep some ice and water at 0 degrees C without adding any heat or taking it away, you can maintain that state for a long, long time. You'll have ice and water together. This is a little bit different from a chemical equilibrium, which we haven't even started talking about yet. A chemical equilibrium occurs when you've got a reaction. So NO2 is nitrogen dioxide. It's one of the components, like what makes smog. And two NO2 molecules will automatically react with each other to make this larger molecule, N2O4, which is, I think that was the more brownish color. That's the one we associate with the color of smog. But this is an equilibrium. Like this constantly goes back and forth. Two NO2s will come together, temporarily make N2O4, and then N2O4 will break apart to make two NO2 molecules. And then this constantly happens. So this is a chemical equilibrium. It's a little bit different from a phase equilibrium, but the concept of equilibrium is the same. Both are in existence at the same time, and they go back and forth. It's not static, it's dynamic. You're always getting this solid goes to liquid, liquid goes to solid. The other thing is when we look at these phase diagrams, we're going to see in a second, we are thinking of a closed system, meaning you're not allowing anything to escape. There's no special circumstances. We're just looking at, okay, if I trapped it all in one little container, what happens to these phases? So this is an example of a phase diagram. And on the x-axis, we have temperature. On the y-axis, we have pressure. And these regions, and they don't have to be colored like this, but these are just to make it a little more clear. These regions denote the three different phases that we are used to: solid, liquid, gas. And so gases tend to occur at higher temperature. So if you naturally look at high temperature, I would expect a gas to occur. That's all this over here. But you can get gases at really low temperature, assuming your pressure is really low. And so this pressure, what does that mean, a pressure? We haven't really talked about gases yet. That means we've got very small amounts of the gas. So as long as there's a very small amount, it's not packed into a container, as long as the pressure's low, you can maintain this gas. Which should make sense, because if I pack in a whole bunch of gas particles close together, I'm starting to make it to a liquid, right? Like that's when these molecules are near each other, that's more like a liquid. So anyway, these lines indicate the phase boundaries. All right, that's pretty clear. And so what you can see is, well, if I want to go from a gas to a liquid, I could have, this is 1 atmosphere pressure, that's standard pressure, that's what we feel right now. If I've got a substance, I think this is water. Yeah, this is water. If I've got water at 110 degrees and I cool it down, oh, look at that. At 100 degrees, it'll start turning into water. And then I cool it down some more, somewhere around 0 degrees. This is 0 right here. 0. It'll turn into a solid. And then if I cool it down further, it'll stay a solid. But I could do a sublimation with water. And the way I would do that is I would lower the pressure of my gas down to here somewhere, and then I would cool it down. And this would stay a gas until I hit this temperature, whatever this is, minus 30, minus 40, something like that. And then suddenly it would turn into a solid without ever going to the liquid stage. Okay? So that's kind of how you read these. If you're right on the line, you're at an equilibrium between the two phases, between solid, liquid, or between liquid gas, or between solid gas. Now, there's a couple of interesting points here. This one right here, the triple point. This is where those the 3 lines meet. The solid, liquid, and gas boundary are kind of all adjacent. And if you're at that point, at that particular temperature and pressure, you have the potential to have all 3 phases existing at the same time. So you can have the steam, the liquid, and the ice all together. The other point is up here, and I want to emphasize that this line ends right there. It doesn't continue. There's nothing above here. Even though the colors are changing, there is no more line, there's no boundary anymore. This line keeps going. It goes off the screen, you can't see it anymore, it keeps going. But this one stops, and where that line stops is called the critical point. And beyond that point, there is no more transition between liquid and gas. So what does that mean? Well, what does a liquid-gas transition normally look like? So liquid to gas, that's boiling. Gas to liquid, that's condensation. You don't see that anymore. You don't see boiling, you don't see condensation when you go, from the yellow side to the green side. What you see instead is some very gradual transition. It was a gas, and then it's slowly turning into something that looks weird, and then it turns into a liquid. So this area up here, it has its own name. It's not a solid, it's not a liquid, it's not a gas. We call it a supercritical fluid. And you might think it's not common. It's actually very common. We don't see it, but we use it a lot in industry. That's how we extract caffeine from coffee. So we take CO2, which is a gas, The other form we know is dry ice. That's a solid. Well, if we take CO2, and I don't have the phase diagram for CO2 here, but if we turn it into a supercritical fluid, it's got some really interesting properties when it's at a supercritical fluid. It actually will allow caffeine to dissolve really easily in this liquid CO2 stuff. So we mix the coffee grounds with the supercritical CO2. We drain this supercritical CO2 that has all the caffeine dissolved in it, and then we let the CO2 evaporate, just like we take the pressure away, it turns back into a gas, and we're left with pure caffeine. So whoever's doing that then sells the caffeine to Coca-Cola, to Monster, to whoever needs caffeine, and then they sell the coffee grounds for decaffeinated coffee, things like that. Although I don't know if that's exactly what they do with decaffeinated coffee, but that's exactly how they get caffeine. Nobody synthesizes caffeine from scratch. They extract it from natural sources. Or they use an alternative, yeah. What's up?
Do you have an example of something that goes from solid to gas, or gas to solid?
Dry ice. So if you take those dry ice pucks, I don't know if you ever throw them in water and they just make all this cloudy vapor. That CO2 is just instantly turning into gas, really cold gas, and then that's causing water in the air to condense. That's what makes the vapor fog-looking stuff. Yeah. So here I got some videos. I'm going to show you some examples of. So this is CO2. Somebody made a cell, and I'll start the playback in a second. But I think already that it's under high pressure. So normally CO2 at regular pressure never makes a liquid. It goes from solid to gas, and that's it. It's below that triple point at our pressure. So in this cell, he made you can put CO2 at high pressure, and so he's managed to make liquid CO2 here. But he is going to, I think, increase the temperature and pressure even more. And notice that, you didn't see any boiling, did you? And then now he releases the pressure back to that. You didn't see any boiling. You didn't see any droplets form. You didn't see any boiling. You didn't see any condensation.
Hey, everyone. I thought I'd show you my latest project.
Yeah. All you saw was, let me start from the beginning. Yeah, so it goes from the liquid line and just kind of turns into this weird nebulous thing that just disappears. Liquid turns into gas, and it's doing it via a supercritical fluid. I think there's another one that I've got that is harder to explain, but it's the same thing. So the black line, there's liquid here, there's gas here for CO2. And here you can see boiling. That's pretty clear. It's boiling. It's turning into gas. That's below the critical point. And then I think what they're going to do. So yeah, they're increasing the temperature. And I think he's going to, whoever's doing this. Oh yeah. So yeah, I think now they've reached the supercritical fluid point. And now then it's condensing again, so now you get the liquid again. It's weird. It's a really weird state. Here's, again, the liquid. Here's the gas. And I think this one, you can see it's still kind of boiling. But instead of, oh yeah, this one's good. So it started out boiling a little bit, but what you would expect is as it boils, the liquid level is going to go down as it turns into a gas. But instead of doing that, that transition just disappears. It just kind of fades away. So that's definitely that supercritical fluid area. You're going from a liquid state to something that's not a liquid or a gas at all. It's just both, a supercritical fluid. Anyway. Weird stuff. Okay. Yeah, any liquid, they all have different phase diagrams. You know, like they'll have different places where they become supercritical fluid. Yeah.
Right. I just assume CO2 is the easiest.
Well, it's an easy gas to acquire. So this one here is a demonstration of the triple point, and this is triple point of water, which you saw, I think, on the diagram was at a lower pressure than we normally are existing at. So 0.006 atmospheres, near freezing. That's where the triple point is. So already you've got liquid water. There's a little bit of ice in there. So you're near some phase boundary, at least for solid to liquid. They're just adjusting the pressure, adjusting the temperature to get right to that point where all three exist. This is at a fast speed right now, so it's going a little faster. You see the bubbling start to happen. There you go. So it's just starting to boil, but you still have ice, you still have water. So you've got all three phases present. And if you can keep this condition perfect, you know, you'll have ice forming here. Everything will be occurring at the same time. So ice will be going to liquid. Some ice will be turning to gas. Some liquid will be turning to ice. Some liquid will be turning to gas. There's a dynamic equilibrium between all the states. Yeah, here you go. Ice boiling at the same time. Really weird. Yeah, it's forming a layer of ice on top, yet it's boiling underneath still. All right. And then, yeah. So this one is a different liquid. This is cyclohexane, which has a lower boiling point than water because it's more nonpolar. There it goes, liquid freezing. Freezing, freezing, not quite frozen yet.
Is the whole thing just gone up? Oh.
And it's boiling. There's bubbling at the bottom. I think this one's a little, yeah, there it goes. Freezing, liquid, boiling at the same time. It's weird.
I was about to say, I think the whole
Are we going to do
thing's
this?
fine. No, it's-
I don't think we, yeah, there, oh, it's so weird. What are they, what? So I believe that this might be at room temperature,
Oh my
and they're
God.
playing, like, I'd have to look up what the triple point is. They might have pre-cooled it or heated it to the right temperature. It might be near room temperature, and they're playing with the pressure. So there's, attached to that flask, there's some kind of vacuum device that is applying the perfect amount of pressure that they need. So they're probably playing with a nozzle that limits how much air gets sucked out, something like that. Yeah. So as far as us being able to do this, well, first of all, we don't have enough vacuum pumps for everybody to use. And learning to use a vacuum pump is a little tricky because you can't just suck gases straight into the vacuum pump because you'll destroy the vacuum pump. Like cyclohexane would dissolve in the oil that's cooling the pump, and then it would destroy the seals. So when you use vacuum pumps to suck things away, you got to have a liquid nitrogen trap. So your pump goes through this little glass thing that gets inserted into liquid nitrogen. So any gases that are being pulled away by the pump pass through liquid nitrogen, and it freezes anything that's in the gas, and it gets stuck in the trap so that the pump doesn't get any stuff sucked into it. It only sucks in just pure like oxygen that would not get trapped by the liquid nitrogen. So it takes a lot more equipment than we have for you guys to do something like this. Maybe we could do a demo, but that would be a big setup. We've got videos. I know it's not as good, but all right. So one more thing I wanted to show about this particular, one more thing I wanted to show about this particular, there's CO2. So the triple point of CO2 is 5 atmospheres. So this is high pressure. So we're at 1 atmosphere. This is 5 times normal, but at negative 57 degrees C. So while it's not exactly easy, you still need a nice setup. You need some kind of cell that can withstand 5 times normal pressure, because you're making a bomb, basically. You can do it. So this is normalus, 1 atmosphere. And so you can see as you increase or decrease the temperature, you go through solid to gas, and that's it. You don't get up here. We don't exist at high enough pressure for this to happen. So here, the other thing I wanted to mention is most phase diagrams look like this one, where the boundary between solid and liquid has a positive slope to it. Only water, I think only water, I can't think of anything else. But let's just say it's rare. Only water has a boundary between solid and liquid that has a negative slope. And that's pretty important because it kind of speaks to the properties of ice. So what happens if you take a container of water, seal it, and stick it in the freezer? It breaks the container. The ice expands. And that's demonstrated here. So the idea is ice takes up more space than water does. The molecules need more room. So if I were to apply pressure to ice, if I were to force the molecules closer together, and that's what I'd be doing if I go up, what happens to the solid? It turns back into a liquid. So ice is weird. If I apply pressure to ice, it'll turn back into a liquid. And that's because naturally water takes more room in the solid phase than it does in the liquid phase. Almost everything else, if I take solid CO2 and I apply pressure to it, it stays solid. Everything else is like that. But water is unique in that sense. The density of ice is lower. It takes up more space than regular water. If that wasn't true, our most fish in lakes would be dead, or they'd be a different kind of thing altogether, because if ice didn't float on water, your lakes would freeze solid over the winter. Instead of having a layer of ice on top, that would insulate the water underneath and keep it liquid. So this is kind of important, the fact that this does this. Okay. So yeah, an increase in pressure favors the phase that occupies less space. And so water as a liquid occupies less space. So if I increase the pressure, it's going to turn back into a liquid. Okay. So what are you going to have to do with these kind of diagrams? Well, you'll have to recognize yourself which area you're looking at is a solid, liquid, and a gas. So I'll take those labels off. So I'll take the gas, liquid, solid. I'll take the triple point label off. I'll take the critical point label off. All you'll have is the axes. And you'll have to tell me, hey, which side is the solid, which side's the liquid, which one's the gas. And the other things you'll have to be able to do is identify what happens to a substance as I heat it from this to this at this pressure. And you'll just have to read the graph and tell me, oh, it goes from a solid to a liquid. Oh, or it goes from solid to gas directly. It's going to depend on the pressure. It's going to depend on the temperature. Okay. So in this case, if I have a solid at whatever that high pressure is, 5 atmospheres of pressure, and I increase the temperature, you would say, oh, it starts as a solid, it turns into a liquid, and then eventually it turns into a gas. And that's what happens when I heat this stuff at 5 atmospheres of pressure, something like that. So you need to be able to label these, and so forth. Okay. So let's try stuff with phase diagrams. I think that's what it is on Chem Activity 25D. And let's see where that is. Oh, you want to see? Sorry. Go ahead. So let's see where that is. 25D. No, oh, thank you. 94? Okay. I mean, it's after that Clausius Clapeyron stuff. Oh, no, it's after 25C. There he goes. So let's try 1 through 8 on page 94.
It's 90. It's 97.
97, sorry. Okay.
What is, oh, Simpson.
Yeah.
What is it? This is 95.
Well, let's see.
I don't know. There's a,
Maybe the questions don't start until 97.
well, there's questions and
Yeah, the questions don't start until after Model 3.
okay.
Some of these questions are pretty easy. Others are a little easier, or a little harder. Well, so how are the phase boundaries represented?
okay.
So like they're represented by these lines, yeah.
Okay, I just want to make sure that I can tell if it was like that simple or not.
Yeah. So the origin of this workbook is almost self-study, self-teaching. Like you learn by reading this.
Oh,
I am helping you along by giving you a big introduction to it. So that's why it seems easy sometimes. But yeah. It's a lot more obvious after we've talked about it.
Is it critical fluid or critical liquid? What was that called?
A supercritical fluid. Yeah, because it's not liquid, but it's fluid like a liquid. So it's, yeah.
7.
Now, does it like
But
change
then,
numbers?
Well, no, it doesn't. Yeah, we'll just continue moving on, and usually with the critical thing we just end it.
Yeah. Okay. Sorry, you're right. Let's see what I had before.
You said that 1 to 8, but
So yeah, I guess it's to 8. Let me make sure mine is the same as yours again. So mine 8, starting at point B. Yeah, in the phase model phase diagram. I don't know if that's what you guys have.
yeah, that's what we have.
Okay. Yeah, it's just 8. Okay. So let's talk about the answers real quick. I was trying to find a phase diagram that would have been interesting, but I couldn't find one. So I think the first couple questions, not hard. If you have a question about them, let me know. But the special at the triple point, everything at the triple point, it's all 3 phases exist in equilibrium. What is special about the critical point? That's different. Anywhere on this line, you'll have both liquid and gas existing in equilibrium. The critical point is the point at which you stop having this phase transition. There's no longer a distinction between liquid and gas anymore. There's this new, past that point, there's a new a new phase we call a supercritical fluid, which has characteristics of both of gas and a liquid. And you can go from gas to liquid past that point, but you won't see any transition. You won't see any, it's not going to boil or condense. It'll just kind of slowly change from one to the other. Yeah.
So like just no actual phase change would just occur?
Yeah, no phase change occurs. It just kind of blends into a gas or vice versa. Yeah, or the reverse. Like you saw that example where, you've got the liquid line, and normally if it boils, the liquid line would go down as the liquid it's turned to a gas. That's not what happened. Just the liquid line just disappeared. And everything turned into a gas. So, what phases are represented at points G and H? Is that what there is? Yeah. So at point G, this is an interesting one. This is actually a triple point. And you can have multiple triple points. Depends on what we're looking at. So this is different from what we've seen before. There's a gas, there's a liquid, and there's 2 different solids. What might this be? It's just different crystal structures. Maybe the metal was FCC and then it turned to BCC or something, depending on, and that's simplifying things. There's many more crystal structures that we haven't learned. But that can happen. So at point G, we have a liquid and 2 different solids, all in equilibrium. At point H, we have a gas and just that solid alpha phase present at the same time. So starting at point A, what happens as you increase the pressure at constant temperature from A to B and then to point C? So that's talking about this. If you're going here, you're starting at a vapor. If you increase the pressure, it's still it's still a vapor at point B. But eventually you cross the liquid vapor boundary and it condenses and it turns into a liquid. So gas to gas, and then it condenses to liquid. Yeah?
Density still being, what is density just being increasing the whole time, basically?
The density, yeah, it should be increasing.
Okay.
So if you're increasing the pressure, you are reducing the amount of empty space there is. Yeah. What's up?
For the base point in G, you said it was a liquid and 2 different solids.
Mm-hmm.
But when I was reading, I don't know, I heard you say earlier that the special point G is all 3 phases.
Well, so you can have more than one triple point. The triple point is not necessarily solid, liquid, gas. That is one triple point. That's one right there. That one is solid, liquid, gas. But as long as it's 3 different phases, that's a triple point. And so the 2 solids plus a liquid also qualifies as a triple point. Yeah. Yep.
What would a thing look like if it was at like that triple point?
Um,
Like how does that work?
I mean, you might have little microcrystals that are, like, you couldn't see. I mean, it'd be powder-like maybe, but you'd be getting two different kinds of crystalline formation. So what I wanted to kind of bring up was, I was trying to look for it, tin. So tin is a metal, and we learned back when we learned crystal structure, most metals do large numbers of coordinations, right? So that's what metals are like. They do FCC or BCC, and that's it. And rarely do they do simple cubic like polonium. Those are all high coordination. Even simple cubic has 6 atoms around it. But then we learned later that tin is in the group 4, and tin can do diamond structure, just like carbon does, just like silicon does, which is, what is the coordination number? It's 4. So how does that make sense? Well, the idea is tin can have multiple solid forms. There is a form of tin, I think the regular form of tin that we would be used to is going to be a more metallic crystal structure. It's going to have a high coordination number. The diamond-like tin, which exists, would be a special case. Maybe at a lower pressure, it exists that way. So that's one example of solids that can have different forms. So, you know, tin in the diamond crystal structure, which has a low coordination number, might not act like a regular metal would. I don't know. I haven't really studied it, but it'll act like the semiconductors do instead. So, you know, you're asking, well, what is it going to look like? Kind of hard to see the solid structure, but if you analyze what the structure looks like, if you analyze what kind of properties they would have, they would be a little bit different. Anyway, so A, starting at point B, what happens when you go point D and point E? So B, here you've got a gas. If you cool it down, which is what's happening, you get condensation from a gas to liquid. And then as you cool it down further, you get freezing. And it turns into a solid with this kind of crystal structure, whatever that is. So I showed you on the slides, that's water, but that's only a small part of water's phase diagram. So it's only showing a very, very narrow view of what water does. Here's a bigger version of water's phase diagram. Oh, it's not. Okay, hold on, I gotta find it. It's in one of my tabs. There we go. So there is a bigger phase diagram for water. So again, it's still temperature on the x-axis. It's still pressure on the y-axis, but it's a bigger range now. And so here's your gas, here's your liquid. Here is the regular solid that we're used to, but look at how many different crystal structures you can make with water. So water, depending on the pressure, depending on the temperature, you can make water have all these different arrangements of molecules in the solid form. It's kind of crazy, but that's how it works. If you're a science fiction fan, there is a famous book. Well, this book's not famous, but the author's famous, Kurt Vonnegut. He wrote a book called Cat's Cradle, which is a stupid name, but and in the story, a scientist has invented a new form of ice. He called it Ice 9, and I can see that Ice 9 is on here. This was before they knew about this. In the science fiction form, Ice 9 was a form of ice that when it got into contact with other water molecules, it would instantly turn that water into Ice 9 as well. And so you can think at any temperature. And so it was a doomsday. It was a book about, the end of the world when somebody throws a piece of Ice 9 into the oceans and causes the oceans to freeze over, kind of thing. So, this kind of idea, was when it was discovered that some science fiction authors wrote about it. But yeah, phase diagram. There are other forms of phase diagrams. So the one we're learning here has temperature versus pressure. That's the only one we're going to look at, and we're not going to look at this crazy one. Don't worry about it. This is just an example. But there are other versions of phase diagrams. So if you're into engineering, material science, there are phase diagrams that instead of having temperature, they'll still have pressure, but then they'll have a mixture of two different metals and see how do the alloy properties change when you have more of this metal versus this metal and stuff. So there's lots of different kinds of phase diagrams, and there's There's a lot that goes into this. But anyway, focus on this. That's what we're going to study. Exactly what you saw in the worksheet. Oh, and here's another one that has multiple crystalline phases, bismuth. So the following phase diagram shows liquid phase in 5 different solids phases, stable above a kilo atmosphere, so 1,000 atmospheres. That's pretty high pressure, up to 300 degrees C. Which solids are stable at 25 degrees C? So once you can make these solids, can you then cool them down and keep them in that phase? Things like that. So I will let you guys look at that later. But these are the kind of questions you could come up with or ask when you have these phase diagrams. So coming back to heating curves. Where's my thing? There it is. Now that we've had time to digest it, if I'm looking at this thing, how many phase transitions are shown on this heating curve? I really need to just tape these to the bench tops, the tabletops. That would be useful. At the bigger universities, they make you buy these,
Wow.
and you have your own. But it's all online. You can like program it and stuff. I think this is better. Well, you also can get an account, and then you can use your phone to do clickers too. Anyway. So we have, let's see. Whoa, we got a couple different answers. So the phase diagrams, the phase transitions only occur in the flat spots. All right, the flat spots right here and right here, where there is no change in temperature. So this is time here, but time here represents heat added. So you've got this flame underneath it, and over time you're adding more heat. So that's what this x-axis represents. So as you're adding heat, what is happening? No temperature is changing. That means a phase transition is occurring. This is solid going to liquid, probably water since this is 0 degrees C. And then you're heating the water, and then another phase transition occurs, liquid to gas. So these flat spots are where the phase transitions occur. Okay. So which phase transition requires more energy?
What are the options?
Oh, I guess A or B. Let's try that. A or B. A, ice melting. B, water boiling. Generally, you could answer this without even looking at this, honestly. So let's start off there. It is the water boiling. It is the B. So in general, it takes more energy to break the IMFs completely. So liquid to gas pretty much always requires more energy. But you can tell from the phase diagram by how wide these points are. If this is a constant heating, so less time is required to melt the substance. A lot more time is required to boil it. And so the boiling requires more heat, more energy, because it takes more time to boil it. Okay. There we go. We already know that. Okay. So before we finish this section, let's kind of focus on water a little bit, since water is so special to us. So these are the unusual properties of water. I mean, they're not so unusual anymore. We know it already. Water has a higher melting point and boiling point than expected. We already can explain why. Hydrogen bonding, that polar OH bond is especially polar. And so we call the interactions with that OH bond, that dipole moment, hydrogen bonding. It expands when it freezes. We haven't really talked about why that occurs, but it's basically how the crystals form. We talked about at least that when you have two water molecules, the way they are arranged is very limited because you need to have the negative side of water near the positive side of another water. That's how they need to arrange themselves. So there's a limited way in which they can pack together. You can't pack them together where two positive sides or two partial negative sides are near each other. And so when they freeze, they have to kind of arrange themselves with a lot of empty space. And so the ice is less dense than water. It's an excellent solvent. It's kind of got one of the best, strongest intermolecular forces, so it dissolves lots of things. Not everything, but it dissolves a lot of things. It's got the largest surface tension of any liquid except for mercury because of the strong IMFs. Mercury's got metal-metal bonding, so that's even better. And because of the strong IMFs, it's got very good capillary action. If I take a very thin piece of glass tubing and I touch it to some water, the water will shoot right up. It's attracted to that glass. I don't need to put any section on it. And this is a little bit unique. We haven't talked about it, although we did mention it briefly. Those heating and cooling curves, the slope of the section where water was absorbing heat and getting hotter, higher temperature as it absorbs heat. Water has a very high specific heat. What does that mean? It takes a lot of energy to change the temperature of water. So like I was saying, if you put a pot of water on a stove and turn the gas on or the heating element on, it takes a while to get to the boiling temperature. But if I take the same amount of metal, same weight amount of metal, and put it on the stove and turn the heat on, that metal will get hot fast because it doesn't take much heat to increase the temperature of a metal. So that's what a high specific heat means. Specific heat capacity is what it's short for. So it retains a lot of energy without changing temperature. Makes it a good insulator, or not insulator, energy storage.
So could you go back for 1 second?
Yep.
Just-
Yep. So here's our nice glaciers that are disappearing. That one might be gone. I have no idea. And it's because ice floats on water. It's because water expands when it freezes. It's got a lower density. That's why glaciers exist. Come on. I mean, this is really weird. Most things as a solid are denser. So water, ice has a lower density than water, but if you compare things like paraffin, these hydrocarbons, liquid paraffin has a lower density than solid paraffin. So solid paraffin will just sink to the bottom of a cup of liquid paraffin, whereas ice floats on top of liquid water. So if we zoom in, we look at a curve of temperature versus density of water. Why is water so weird? Well, if I heat up water, normally the density goes down. And that should make sense to you because if I take some molecules in liquid form, they're kind of close to each other. How close to each other is going to define how dense they are. The closer they are, the denser it's going to be. But if I heat up water, you can imagine the molecules are moving more quickly. And their ability to stay close is probably not as good. So it should make sense to you that as you heat up water, the density is going to drop a little bit. Okay? But if you look at the very first part of this curve, if we zoom in on that section up there, that's what it looks like, zoomed in. And this is where water's a little bit weird. So if I start with water that is just melted, and I increase the temperature slightly, the density increases, which is weird. And the reason for that is, well, you've got these ice crystals where your water is in these perfect arrangements of water molecules. There's a lot of empty space because it's in solid form. As soon as they melt, they barely have enough energy. They'll kind of stay in the same position. But once you melt them and they're not perfectly stuck in those positions, you give them a little bit of extra energy, a little bit more kinetic energy. Well, those water molecules are going to fill in the gaps, and they're going to get slightly denser as a result. They're going to get closer together because they can. But then at some point now, more energy, now they're moving too quickly. They can't stay that close together, and now they'll do what normally they'll do, is they'll get less dense, like everything else does. Okay? So water's unusual. Water is a special case. It's got all these weird things happening to it that makes life the way it is. I mean, this is kind of subjective, but we call water called the universal solvent, meaning if it's universal, it should mean it can dissolve anything, and it can't. But it can dissolve more substances than any other liquid. We can put sugar, an organic compound in water. We can dissolve salt, an inorganic compound in water. It takes all these nutrients with it, wherever it goes. It's got great capillary action. Here's a nice picture that shows capillary action. So what this is you've got this general glass tube of water at a right angle, and it's filled with water up to here. And what these are these little skinny glass tubes. And as you go to the right, they get skinnier and skinnier. If everything was normal, if there was no capillary action, then the level of water would be the same in every single tube, right? That's how gravity works. But because water is really attracted to glass, and these glass walls are so close together, the water actually climbs up higher. And as the tube walls are closer and closer together, the water climbs up even higher. That's capillary action, and like you could see it there. So here it's filled up because of gravity. We've filled this thing up with water. That's where it is. Without capillary action, these should all be at the same height. The fact that they're higher in the tubes is because water is attracted to the glass surface. So they just travel up a little bit. And this is how water moves through plant roots and leaves, and it's how you have tiny capillaries that bring blood to every part of your body. The heart really only works for the big blood vessels, right? The big arteries and veins. The way that your blood gets everywhere else, the little tiny cells through the capillaries, is capillary action. The heart has nothing to do with that. The heart just moves the large quantities. That's it. So we talked about high specific heat capacity, usually shortened to specific heat. Here's the formal definition. A specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree. So here are some numbers. Water has the highest heat capacity out of this list. So the idea is it takes 4 joules of energy, approximately 4 joules of energy, to heat up 1 gram of water by 1 degree C. It's a lot of energy. Compare that to copper. If I have a gram of copper and I wanted to increase the temperature by 1 degree C, it only takes 0.4 joules of energy. 10 times less, more than 10 times less. So that's what we mean by water has a high heat capacity. Think of water as a good energy sink. You can store a lot of heat energy in water. Yeah?
Are they trying to use it to store solar energy or anything?
Maybe.
It's just, yeah.
So
It's like-
I know that a very efficient way of heating water in your home is to make, you get PVC pipes and just run it zigzag across your roof, and you run water through that, and the sun will heat up the water, and it'll stay hot for a while. I mean, you can use that for showers and stuff if you want to avoid having to have a heater heat your water all the time. The problem with storing energy in water is I don't know how you could get it back out easily. So, I mean, yeah, it is a good energy storage solution. You can, let's put it this way. If you ever thought and most of you probably haven't, if you ever thought about what would it be like to own a hot tub, it takes a lot of power to heat those up. A regular outlet puts out 110 volts, 120 volts, something like that. A single outlet with the amount of current that's allowed to go through it, would take forever, like to heat up any small amount of water. You need 4 times that amount of power for a hot tub. So like you need special circuits, you need an electrician to come out. Water takes a lot of energy to heat up. Let's put it that way. It's very, very not practical. All right. But what happens, and this is actually important, I'm not a big climate person, but the fact that water stores so much energy, or can store so much energy, is it moderates temperatures in the Earth very, very easily. So, you get warm spells, all of that water around that area will absorb all this heat, and then when it turns cold again, the latent heat that's still in the water is there. Better than the Earth at storing energy. Water is so much better. So anyway, just kind of wanted to show that. That is, we have all this information now. We can understand how amazing water is. So what I want to work on next is a completely new topic. We're going to talk about gases. So we'll get into pressure. And we'll use pressure and other properties to talk about how gases behave. So we've already started talking about it, but we'll do a lot more detail now. So let's start with how we describe a gas completely. So liquids and solids are a lot easier because you can weigh a solid and have a mass, and that's really all you need. Same with a liquid. You could weigh a liquid, have a mass, you're good. You can't really get the mass of a gas very easily. All right, it's harder to weigh gases. You can weigh them, it's possible, but it's very difficult to do that. So other ways of describing a gas is using this method. You have to have 3 of these in order to completely describe a gas that you have. So the 3 properties that you need to know about are volume, temperature, pressure, and number of particles. So you need 3 out of these 4 to completely describe a gas, the state of a gas. Let's put it that way. So our units of pressure, we've already talked about atmospheres. And while this is a very common unit in science, it's very convenient, the technical SI unit, the System International Unit, is the Pascal. So what does that mean? Well, the Pascal is a derived unit. You can break the Pascal down into kilograms and meters and seconds. I think it's a kilogram. Is it a kilogram meters squared per second? I can't remember, but we'll see it in a second. So just to remind you, and let me go back. Liters is going to be our standard unit for volume. So almost everywhere we're going to be using liters. There are cases when you don't have to use liters, but if you want to be safe, use liters. If you're not sure, use liters. Temperature has to be in Kelvin. There is no alternative to that. Even though Celsius is a metric unit, it is not the SI unit. And we have to use Kelvin for any temperature describing a gas. And we'll talk about that in a second. Mole, of course, is the standard. How many particles do we have, right? We're going to use moles instead of actual numbers of gas atoms or something like that. So just to remind you, Kelvin is an absolute temperature, meaning 0 is the lowest you can have. That's where it starts. Everything else is a relative temperature. It's relative to that. But Kelvin is not difficult to hopefully understand. It uses the same scale as Celsius. A 100-degree change in Celsius, 0 to 100, is the same in Kelvin. So Kelvin water freezes at 273, and it boils at 373. That's a 100-degree change. So the difference in temperature is the same between Kelvin and Celsius. They just start at different numbers. Fahrenheit sucks. Don't ever use Fahrenheit. But I know we use it for weather here. We're used to it, but it sucks in science, so don't ever use it. you should know how to convert. And so the conversion, and I'll give these to you, don't worry, you don't have to memorize it. And I keep meaning to fix this slide, but I prefer Kelvin is degrees Celsius plus 273.15. That's an exact conversion. So the 0.15, that's it. That's all you need to make it an exact conversion. You don't have to worry about the sig figs of this anymore. It's just whatever you start with for Celsius or Kelvin. These two, for Celsius to Fahrenheit, these are also exact conversions. All right, so the 32 is infinite sig figs, the 5/9 is infinite sig figs. You just have to worry about what you plug in. That's it. And like I said, maybe I'll ask you a question on a conversion, but I'm never going to, I won't say never, but I hate putting, a problem that is something unrelated to conversion where I give you Fahrenheit, because nobody uses Fahrenheit in science, so you shouldn't get that. All right, so there we go. Here is pressure. Let's talk about what pressure is, because we kind of just hand-waved it earlier and said pressure is proportional to the number of gas particles you have. Yeah, that's true. But let's talk about what pressure is. We use the Pascal, that's the SI unit. And a Pascal is technically a Newton per meter squared. Well, you might ask, what is a Newton? A Newton is a unit of force. And force is in the numerator. What's in the denominator? Meter squared? It's an area. Length times length. That's an area. So what a pressure unit is a force applied over an area. That's technically what it is. And the visual example I like to give people is, imagine you're lying on a mattress and your body weight is a force. It's, your body weight is applying a force on the mattress, but it's applying that force, that Newton amount, whatever it is, over a large area, the entire surface of your body lying on the mattress. And so the pressure you're applying to the mattress is low because you've got a large denominator, your large body is lying on the mattress, and so the pressure is low. The pressure on the mattress is low. But if I contrast that with standing on a mattress, I have the same force, your body weight, but now it's being applied over a tiny area, the soles of your feet. And so the same force over a much smaller area will give you a larger pressure. And the way you can see that is how far do you sink in the mattress when you're standing on it versus how far do you sink in the mattress when you're lying on it. All right, that's kind of how I like to think of pressure, okay? Honestly, that's not the same as a gas. So let's try to talk about it in terms of a gas. Well, the atmosphere is applying a pressure to us right now. If you think of how much air is directly above your head, that weight of that air is applying a force over that area over your head, and that's the pressure you're feeling. The closer you are to space, the higher on a mountain you are, the less air there is. So the less weight of air there is over your head, the less pressure you're going to feel. So that's what pressure is. And we have so many units: millimeters of mercury, torr, which are the same technically, Pascal. And notice that the conversion between Pascal and torr, or Pascal and atmospheres, there's a large number of pascals. So even though that's the SI unit, we normally see it as a kilopascal to make it a more readable number. So 1 atmosphere is 101.325 kilopascals. So don't need to memorize these conversions, but I can encourage you to at least memorize the 760 millimeters of mercury one, just so that in your head you know, oh, that's standard atmospheric pressure. You don't have to think about it too much. Okay. So anyway, that's standard atmospheric pressure. Those are the conversions between all these different pressure units. And how do we measure pressure? So I showed you a manometer before. This is a little bit different. This is a barometer. This is how we measure atmospheric pressure. And the way this works is you take a test tube that's really long, and you fill it completely with mercury. And let's say you take that tube that's filled to the brim with mercury, put your thumb over it, and then turn it upside down so nothing spills out with your thumb over it, and then stick it in this pool of mercury. So what'll happen? Well, gravity will start to pull this mercury out of the tube. It wants to be level with the rest of the water, the mercury in this pool, okay? What's left in here when this mercury drops out? Nothing. There's a vacuum. There was nothing. I mean, there was mercury there. How is air going to get in there? Air's not going to get in there. Well, what stops all of this mercury from running out? The naive answer, which is what a lot of people will say, oh, there's a vacuum. The vacuum stops it. Like, you don't want to generate a vacuum. Well, a vacuum is nothing. The vacuum is not doing the stopping. The vacuum doesn't stop the mercury from coming out. What stops the mercury from coming out is the atmosphere. So it's hard to think about it, but the atmosphere is pushing on the surface of this mercury. Right? The weight of the air that's naturally existing in this, wherever I have this pool of mercury, there's a weight of air that's sitting on top of this mercury. When this is draining, what happens to the level of the mercury in this pool? It's slowly going up. So if this were to drain all the way, the pool would go up. Well, that's going against what the atmosphere is doing. The atmosphere is pushing down. So there is a balance between gravity here. You know, the gravity wants to pull this mercury down to keep it level. And then the atmosphere is pushing back. The atmosphere is pushing this pool of mercury down. It wants to push it down. So there is a balance. And when it reaches that balance, this mercury will be at a certain height. What's the height going to be? 760 millimeters. That's how high this column is going to be. That's 76 centimeters, in case you think better in centimeters. So a meter stick, here's a meter stick. It's going to be that tall, right here. That's close, not quite to its life size. So that's how high this mercury will go. If there's bad weather, then the atmospheric pressure will go down. And what will happen, there's less force on this mercury pool, and so this mercury will drop. It's going to be able to drop down. The pool of mercury is going to rise. I forget meteorology. I don't know with bad. So I guess bad weather, you can have low pressure and high pressure. But yeah, the pressure of the atmosphere changes based on the weather. And so the height of this column of mercury goes up and down. And that's what they give you when they give you the weather report. What's the barometer reading? It's so many inches of mercury. So instead of millimeters or centimeters, they give you inches, but it's the same idea. So that's a barometer. That's the old school barometer. It uses mercury. We don't do that anymore, but that's how we used to measure it. If you were to make a barometer using water, you could do it. But mercury is so dense and heavy that that's how high the column would be. The gravity's pulling in the mercury. If I tried to make a barometer out of water, I would need a tube that's at least 33 feet high, because it would take that much water to kind of counteract the push of the atmosphere on the pool of water below it. So you could make a barometer with water, but it would take a huge barometer to do it. So there's the manometer again. So barometers are only for measuring atmospheric pressure. A manometer is the old school tool for measuring the pressure of some gas container. So here we have a U-shaped tube, and normally if this was not connected, I would have atmosphere pushing over here, and I would have atmosphere pushing over here. Equal pressure, so the level of mercury is going to be the same on both sides. Let's say I hook up a gas container to this side of the manometer, and the levels don't change. Well, that means that the pressure of gas in here is exactly the same as the atmospheric pressure. But let's say that the pressure of the gas in my container is higher than atmospheric pressure. Well, then this gas will push on this level of mercury harder. The atmosphere can't push back as hard, and so you'll get this imbalance. And this difference in height is the difference in pressure between the atmospheric pressure and the pressure in the container. So how do we know? Well, what's the pressure inside here? It's going to be whatever the atmospheric pressure is plus that extra difference in pressure. So atmospheric pressure is 760 millimeters of mercury, and then I add whatever millimeters of mercury I have here. That'll give me the pressure of the gas. Well, what if the pressure of the gas is lower? Well, if this pressure inside here is lower than the atmospheric pressure, then you'll get the opposite happen. The atmosphere will push harder, this level of mercury will go down, this one will go up, and you'll still have a change, but the change will be a negative change. It'll be the opposite. So the pressure inside here is going to be the atmospheric pressure minus whatever this height is. So you have to be really careful about what your change in pressure is, if it's a positive change or a negative change. Okay? So it should make sense. If this is lower in pressure, if this is not, if this is a higher level, then that's going to be lower pressure. You're going to be subtracting from atmospheric pressure. If this is higher, like this, then you're going to be adding to the atmospheric pressure to get the pressure of the gas inside. This is what is known as an open-ended manometer. The manometer on the other side is exposed to the atmosphere. Okay. So here, let me ask you to try this one real quick. I have a manometer hooked up to a gas container, and that's what the height difference is. What is the pressure inside that gas container if the atmospheric pressure is currently reading 750 millimeters of mercury? It's like a stormy day or something. Go slow. All right, let's stop it at 1. Okay. So, I know what's going to happen. All right, most people voted B. And if you voted B, you'd be wrong. So why were you wrong? Which is it's fine. This is going to happen. Notice the units. The height of the mercury is 25 centimeters. Well, these pressure units come from literally the height of the mercury column, and they're in millimeters. So you need to have identical units. So if the 750 millimeters of mercury, that is 250 millimeters. So 750 plus 250 is 1,000 millimeters. And you add because this one is pushing harder, that's a higher pressure. Okay? So pay attention to the units. The pressure units, the original ones, are literally length units. Okay. We might as well do this just to slow down a little bit at the end. Make sure you know how to do conversions. Just to make sure, let's do a couple conversions. What is the pressure in atmospheres represented by 722 millimeters of mercury? So to convert this, you need a conversion factor where millimeters of mercury cancels out. And since I'm trying to get atmospheres, I need atmospheres in my numerator. And then I look up my qualities. Well, 1 atmosphere is 760 millimeters of mercury. So that will cancel. And it's just telling you you divide, and you will get 0.950 atmospheres, so 3 sig figs. If I have kilopascal, I have atmospheres and I want kilopascals instead, 0.63 atmospheres. I want atmospheres to go away, so I'm going to put my denominator. I want kilopascals instead. 1 atmosphere is 101.325 kilopascals. That's an exact conversion. So you don't have to worry about sig figs here. But that has 2 sig figs. So when I do my conversion, I get 2 sig figs, 64 kilopascals. All right, so those aren't too bad. Again, you don't have to memorize those, but because just know how to do the conversions. There's another unit we didn't talk about, PSI. PSI stands for pounds per square inch. Pounds, well, we think of it as a weight or a mass. It's not a mass. Or they've redefined what pounds is a couple times. But pounds used to be considered a force. And so force over square inches, area, that's a pressure. So PSI is another pressure. Let's stop here. So next we will start talking about all the gas laws, which you may have seen before. This is kind of one of those things that they always teach in high school chemistry because they're easy to talk about. But we're going to go over the gas laws, the basic ones. Then we'll get to the ideal gas law. We'll talk about kinetic molecular theory, and we'll start making it complicated by doing partial pressures, mixing gases together, and there's a lot of word problems in gas law stuff. So that's where it's going to get a little tricky, is when you start doing the math problems. So we'll start next week, and we'll stop this here. Okay? All right. Yeah.